Swayam Prabha. Digital India. Educated India.
We have discussed a lot about the soil characteristics, and we have devised different types of strategies to understand how the origin of soil occurs, how soils get redeposited, and how they are classified based on their redeposition and the transportation agency. Later on we talked about some indices which characterize the soil mass, and they were Atterberg limits. That in short was the interaction of the soil with water, and we wanted to study what really happens when soils come in contact with water. From there on we moved to discuss about the compaction characteristics of soils, and this was the first time when we talked about how the microstructure or the porous structure changes because of the external impact of the loads or the stresses. Then we talked about the seepage characteristics, and then we tried to understand based on the coefficient of permeability how the soils can be characterized. I am sure you must be realizing that all these discussions which we had done until now are valid for characterization of the soil mass. Subsequently, we talked about the stress which develops because of the external loading in the soil mass, and this is where the compressibility comes in picture. That means, when the soil mass is exposed to external loading, how it responds, and this could be a sort of an engineering behavior. So, I am sure the common thread between all these discussions which we had until now is to understand the response of the soil mass to the external stimuli or to the fluids or to the pressures which are being exerted on them. So, in today's lecture I will be discussing about the compressibility characteristics of the soil mass, and what I have written over here is this is compressibility and consolidation, because once we have understood the compressibility characteristics of the soils, we will move on to discuss about the consolidation characteristics of the soils. As the name suggests, the compressibility is the compression undergone by the soil mass, and this is mostly because of the external loading. In the previous lecture we have talked about how the stresses can be computed in the soil mass because of the external loading. Now, if I consider the compression of the soil mass, this is normally we talk about, or we are interested in, the volumetric compression. Now, volumetric compression of the soil mass would depend upon the state of the soil mass, and the type of loading which acts on it. We have already studied the type of the loadings. This could be the point load, this could be the uniformly distributed load, this could be different types of loadings which we have talked about in the previous lecture. Now, as far as the state of the soil mass is concerned, normally we deal with a dry state. It could be a partially saturated state, or it could be a completely saturated state. So, when we define the compression characteristics of the soil mass, it becomes important for us to understand soil is in what state, dry state, partially saturated state, or the saturated state. Now, suppose if I consider a surface, this is the ground surface, let us say, and there is some loading which is coming on the top of this. So, normally we say that this is delta sigma. Now, delta sigma is the one because of the construction of this facility over here. Now, if the soil mass happens to be dry, what is going to happen? The compression is going to be due to the expulsion of air. Why? Because air is compressible. Okay, as compared to the soil grains which are incompressible. And so is water also. If I am dealing with the dry soil and if I load the dry soil system, the chances are that the air will being compressible will go out, but the soil grains which are incompressible is not going to be deformed. Alright. However, when I change the scenario, I will be talking about the third case directly, that is when you have the saturated state of the soil. This is because of the expulsion of water. The volumetric deformation is going to occur. Okay, because water is incompressible and it takes time to move out of the pores and there is a time lag. That means this process of expulsion of water from the soil pores is going to be a function of time, and this is mostly because of the fact that hydraulic conductivities of the geomaterials are extremely small. Particularly for the fine grained soils. Alright. So, the situation is like this, that the moment you load the system of soil mass from outside in the form of delta sigma, the amount of some air may expel out and there could be a compression. The major contribution of the compression is going to come because of this process, and hence we say that volumetric deformation of the soil mass is going to take place because of either the expulsion of air, expulsion of water, or the third one could be the compression of or reorientation of soil grains. Alright. So, these are three responsible factors. Now, when I was talking about the particulate nature of the soil, I had this small model that suppose there is a loading P which delegates to sigma, and I had talked about two situations. Suppose this is the soil mass and the lateral sides are unconfined, alright. So, this is the unconfined soil mass. If I keep on increasing the intensity of the load, say from P to Pn, where Pn is greater than Pn minus 1, is greater than Pn minus 2, is greater than P, what is going to happen? If I do not have a confinement, the tendency of the particles would be to first, the whole soil mass will get compressed, and then because there is no confinement, the tendency of the soil mass is to flow out. So, if I restrict Pn to such a limit that Pn itself is less than the yield strength of the soil. Now, we do not write sigma y over here, we will be writing the shear stress. So, suppose if I say the shear stress y, alright. In this case, only the compression is going to take place. Why? Because the shear strength of the soil is higher as compared to the stresses which are getting delegated into it, and hence there is no slippage, there is no rolling over, there is no reorientation of the particles, and hence this is a pure case of the compression. This is what actually we are going to study today, A part. However, if reverse is true, and if I say Pn creates a stress which is greater than the yield strength of the soil, this becomes a shear strength analysis. So, shear strength dominates the mechanism of load transfer. Hope this part is clear to you. So, part number B we are going to do in the second course. This will be dealt with under shear strength theory, and not today. However, the part 1 A will carry on with the discussion on A. That means, we are restricting to a situation where the state of stress in the soil mass because of the external loading is not going to exceed the yield shear strength, alright, and hence the compression only is going to govern the process. Is this part okay? Oh, this is the P, that means the load, and if you compute the stresses along with this, this will be sigma n greater than sigma n minus 1 to sigma. So, these are the stresses, these are the loads. Below this is the yield strength of the soil, yield shear strength of the soil, alright. So, coming back to the issue, see what we have done until now is, we have defined the compressibility in such a manner that this is the fundamental characteristics of the soils and its engineering property, and it basically tells you about the response of the soil mass to the external loading. A follow up of this would be the consolidation process, which we will be discussing in the subsequent lecture. So, this is how actually the compression has to be defined. Now, what I intend to do in today's discussion is, I will be talking about how to quantify the compressibility characteristics of the soils. So, the question is, how would you obtain the compressibility of the soils? So, that is the determination of compressibility characteristics. Of the soil mass. There are two ways. The first method is which is known as a oedometer test. We call it as oedometer test. Find out what is the meaning of the word oed. So, this is a hollow ring of steel, stainless steel, normally 75 mm in diameter and 25 mm in height, and made up of about 0.5 mm thick metal. Now, this is the oedometer ring. Oed is basically a sort of happiness. So, the name is a interesting name. This is what is known as a oedometer ring. Alright. So, this is a stiff stainless steel hollow ring of dimension 75 mm and 25 mm. Sometimes people use 50 mm diameter, and the moment it becomes 50, this will become 20 mm. So, these are the standard things. So, one is by conducting the oedometer test and filling the soil sample in this ring and then applying a normal stress. Alright. So, sigma is the stress which is applied on the soil sample, which is contained in a hollow ring which is made up of steel. Now, steel gives enough stiffness, and hence the radial strains in this sample tend to 0. That means there is no deformation of the steel ring. So, when you apply the load on the soil mass, there is no radial deformation taking place in the system. So, this becomes a opposite case where we had talked about the unconfined. This becomes a confined boundary, and when confined boundary is there, this is what gets simulated with the oedometer ring. When I load it, the only possibility is that the soil grains are going to get compressed. There is not going to be a shear failure. There is not going to be any rolling, and there is slippage along the plates of the fine grained materials. Now, unfortunately, this is not a very realistic situation. Because most of the situations which prevail in the nature or in practice are 3-dimensional. I hope you can realize that this is a 1-dimensional loading and 1-dimensional deformation of the sample. So, that means if I keep my sample like this, so if this is the sample to begin with, the moment I have loaded it, and normally rather than having a point load, what we do is we distribute this load on the surface. So, this is how the P load is acting, which gives a sigma stress. Now, this is not a very realistic situation. So, in order to create a realistic situation, what we can do is we can obtain the compressibility characteristics by doing a triaxial testing. So, this is 3-dimensional in nature. What we do is we take a cylindrical sample. So, this is the cylindrical sample. You must have noticed here what we call is as the diameter d, and this is the height of the sample h. So, we maintain d by h ratio as 3. Alright. This is what the typical situation is, and I hope you can realize that why dA by h is kept as 3, because in the previous lecture when we were talking about the stress which is getting induced into the soil mass, when your dimension of the loaded area is 3 times the height of the sample, all the stress bulbs which are going to get confined into the sample would be 99%. You got this? So, geometrically we force all the pressure bulbs to remain confined in this system, and hence I can assume that the loading is uniform on the sample from top to bottom. Clear? That is the reason. So, when we do triaxial testing, we apply, let us say, sigma 1 over here, sigma 2 over here, and then sigma 3 over here. Normally we maintain sigma 3 equal to sigma 2. So, this also becomes a biaxial testing, but it is in 3 dimension. When we will be talking about the triaxial test for obtaining the shear strength characteristics of the soil mass. So, let us again remain confined to odometer test, which is 1 dimensional in nature. Okay. And as I discussed, when you apply this stress over here, so the deformed sample would look like this. This is the deformed sample, and I can say that there is a deformation of, let us say, delta h, and delta h is the reduction in height of the specimen of the soil, because we have taken some small portion of the soil mass, we have fitted in the ring, and then we are trying to find out how the compression characteristics look like. Now, delta H is the compression also. So, rather than writing reduction in better scientific language, this can be replaced with the compression. What is the significance of this? If you have a soil mass, and suppose if I lay a foundation on the top of this, alright. So, this much of this compression of the soil we are going to observe due to external loading, provided the soil is same. So, this soil is same as what you have in the nature. You have taken out some sample over here, filled in the ring. Either I can remold this sample, or I can take rings which I can insert into the soil mass, I can take them out, and this is how we can collect a undisturbed sample, and that sample can be inserted into the loading frame, and I can load it and I can get the deformation. Fine. So, this becomes the odometer testing, which is what we are going to discuss in today's class. So, let me discuss a bit about the one dimensional oedometer test or the consolidation test we call it. There are two methods of doing the analysis. Particularly when we are working with fine grained materials like either clays, or you might be having silts, or you might be having clay silts or silty clays, so on. Normally, we do not talk about the compressibility characteristics of the coarse grained materials, because as I said, the grains are incompressible, and hence there is no point in talking about the compressibility of the dry soils, particularly the granular material. So, when we talk about the fine grained soils, in order to simplify things, what we do is we saturate them. How saturation is done? This ring, which is containing the specimen of soil, normally this is placed in a on a pad in such a manner that this pad has a groove in it, alright. So, this is what is known as base plate, and this base plate is connected with a drainage tube or the drainage. We call this as a drainage port, and this drainage port can be connected to a water column. Fine. What we do is, in order to spread the load which is coming on the sample, we put it on porous stones. So, we place porous stones in this groove. This is the porous stone, and one similar porous stone is kept on the top of the specimen which is contained in the ring. So, if I show you the ring like this, in which the specimen is contained, so this is the oedometer ring, with a specimen of the soil mass. We will put a porous stone at the top also. So, this is porous stone number 2. Or you can say top and bottom. Alright. On the top of this porous stone comes a loading pad, this is made up of steel, and there is a groove in which I can keep a ball. So, this is the loading cap, and this is the ball which is made up of steel, stainless steel, and this is connected to, entire thing is connected to a load frame. So, this is the loading pattern, or sorry, loading assembly we can call it. So, this is the machine or the loading frame. I can read how much load I have applied, or I can devise a system by which I can apply a certain known amount of the load on the plate. I also attach a dial gauge over here, and this dial gauge gives us the deformation undergone by the specimen when it is loaded. So, dial gauge is DG, is used for obtaining the delta H. Alright. So, dial gauge gives you the readings that after you applied the stress on the sample or the load, how much the deformation the specimen is going on, that is delta H. And I hope you can realize that area of cross section remains constant. Of the specimen remains constant, and hence delta H is also equivalent to delta V, the volume. Now, choice is mine. If I want to do a study on a dry sample, I can do it. You can prepare the sample, you can take dry soil, you can pack it in the odometer ring, and you can apply stressors and you can obtain delta H. I can vary the moisture content of the fine grained materials, and I can fix them in the odometer ring, and I can study the compressibility characteristics. Normally, when we deal with the fine grained soils, as I was saying, to make life easy, we saturate it, we make sure that the sample remains saturated always. So, when we do this test, we open the valve and we allow water to remain always filled up in a container which is a bath. So, this becomes the water bath, and this remains flooded with, in fact, the water bath should be up to the higher limits of the specimen. So, the water can be maintained up to here. So, sample remains or the specimen remains submerged in water all the time, and hence we are ensuring that we are obtaining the saturated state deformation characteristics, compressibility characteristics of fine grained soils in particular. We should do this test to understand things better, or maybe see some videos where these type of demonstrations have been done. So, as far as the analysis of test results is concerned, basically what I want to do is, I want to obtain a relationship between the void ratio and sigma prime. So, sigma prime is in kg per centimeter square, sometimes we also write it in kPa. Void ratio is going to be in percentage, and whatever relationship I get, this becomes the compressibility characteristics. Okay. There are two methods of doing this test. The first one is where at the end of the test so when I say at the end of the test, it is understood that the objective or the target effective stress level has been exposed to the sample. Normally effective stress is exposed on the sample in steps. So when we say at the end of the test, that means number of loadings which are normally doubled. So suppose if you start with sigma prime, 2 times sigma prime, 4 times sigma prime, 8 times sigma prime, 16 times sigma prime, and so on. And between the each loading, incremental loading, we wait for 24 hours for the dial gauge readings to stabilize. In other words, we give 24 hours of waiting time for specimen to undergo the maximum possible deformation, alright, or the compression. So we can find out how much sigma prime is required, that much load you have to apply, because sigma is the area of cross section multiplied by sigma prime will be the loading. So normally you take first load, 2 times second loading, and so on. So at the end of the test, that means once the number of loadings have been achieved, you find out the moisture content. How it is done? Suppose if I am a designer and I want to design, let us say, an embankment which is going to be coming on the ground surface. So remember, what we have done is we have obtained the stresses coming at this point because of the external loading. So that is delta sigma. So this becomes my design stress. Okay. So this design stress I am going to expose onto the specimen to get its response, and hence I know what is the total magnitude of delta sigma which I have to apply on the specimen. I can break it small cycles, number of cycles or number of steps. So I can apply delta sigma by n and follow this pattern of 2 times of the loading, which is the standard procedure, and complete the test. So once the test is over, you remove the specimen containing, you remove the ring containing the specimen and weigh it and find out its moisture content. So suppose this moisture content is W. In the second procedure, what we do is at the end of the test, take out the ring containing the specimen and dry it up and find out the dry weight of the specimen, which is Ws. So these are two methods, fine. So in the first method, when we are dealing with moisture content, if specific gravity is known multiplied by moisture content, this will give me S into E. Now I am making sure that the specimen remains saturated all the time by doing this arrangement of water bath, and water bath remains filled up with water, specimen remains saturated. So S is 1 That means the void ratios are G into W. If I know the initial void ratio E naught, this is the final one after the test. So, if I say that delta E is E naught minus EF, clear, and making sure that I am doing one dimensional analysis, if you remember here, area of cross section is constant. So, I can say that delta V upon V, the volumetric strains which the sample or the specimen has undergone are equal to delta H upon H, where H is the initial height. So, suppose if I replace this by capital H, and delta H is the change in height of the sample, this will be equal to delta E over 1 plus E naught. So, this is a relationship which can be utilized. So, here what I have done, I have got the final void ratios, I know the initial void ratios, delta H can be obtained at every change of stress. So, if I try to recomplete or complete this graph, I know the initial void ratio which is known at a very small stress, we call this as the sitting load or the seating pressure. This is just to maintain the contact between the sample and the top plate, complete, because if you do not allow any seating load, there will be initial disruption in the readings. So, this is the point from where we are starting the compression process. So, suppose if you take the first increment of the load sigma 1 prime y prime, because the sample is saturated and submerged, clear. So, you have to reduce the pore pressures and compute the sigma 1 prime, but I am sure you must be realizing when we are doing the oedometer test and we have put porous stones at top and bottom, we are ensuring that the pore pressure does not remain contained in the specimen and gets dissipated. So, basically U turns out to be 0 and hence sigma prime is same as sigma. So, this is how the relationship would look like. Okay. So, this is the function which I have created from E value. Now, how would you get E from this relationship? So, delta E will be equal to 1 plus E naught into delta H upon H. E naught is known, change in height of the specimen which can be obtained directly from the dial gauge reading, and I know the initial height of the sample, I can compute delta E, and from there I can back compute starting from this point to this point, I can fix the relationship. So, once I have E versus sigma prime relationship, I will tell you how to do analysis further. The second method is, at the end of the test you find out the dry weight of the specimen, which is Ws. So, if I know the Ws, Ws, this thing divided by area of cross section multiplied by G into gamma W, what this value will be? Sorry, very good. So, this will be the H final, is this correct? Nice. Why? Because once the test is over, you have taken out the whole thing, you can subtract the weight of the ring from the total dried weight of the specimen, you get Ws of the specimen, Ws, this is the area of cross section, and G into gamma W is the density, clear. So, weight upon density is multiplied by area of cross section will be the height term. So, HF I have obtained. I hope you can realize we have fixed this dial gauge to get the change in the H value, and what I am getting from here is final HF. So, at each incremental loading I know the value of H also. So, this can also be utilized to compute the void ratios by using this relationship. Choice is yours, whatever you find easy can be utilized. So, nothing is changing except for Ws, the weight is corresponding to the final stage, so HF is fixed. So, in most of these situations what we do is after getting the final point we back traverse to the initial value. So, HF once you have obtained, delta HF will be equal to H naught minus HF, clear. Now, delta V upon V is the volumetric strain, which is same as the vertical strain the sample or the strain the sample, which is equal to change in void ratios upon 1 plus E naught. If you remember, when we were talking about the 3-phase system of the soil, we had used 1 plus E naught term as a specific volume. Okay. So, it is a sort of a normalization of the change in the void ratios undergone by the system because of the compression for a specific volume of 1 plus E naught. So, this is how you normalize the things. So, 1 plus E naught is a normalization parameter which is known as a specific volume. So, implicitly what we are not plotting on these scales is, I hope you can understand, the time, because each step is a function of time. So, this time we assume to be 24 hours and we make sure that the dial gauge readings have subsided. Normally the practice is you keep on observing 3 to 4 dial gauge readings, and once they are constant we can go for the incremental loading or unloading. So, if 3 dial gauge readings are constant, we assume that the sample has equilibrated. Clear? Done? Any questions? These tests look very simple, but you will be surprised to know that till date the profession depends upon these tests to get the correlation between what is happening in the field once you have taken a sample out from down below and testing it in the laboratory. There is no other way to do the analysis of what has caused the failure of the geotechnical structures, foundations, embankments, any structure which you are making out of it. Now, I would like to interpret this graph further because this is the crux of the things. So, what we have done is by conducting these experiments, we have got a relationship between void ratio and applied stress. So, let us do the analysis of these relationships and see what all can be deciphered from here. So, typically we get a relationship like this, what I have shown there. If I plot E versus sigma prime, this is the initial compression curve, alright. At this point, which is corresponding to a certain sigma prime value, if I stop loading the sample and if I unload it, reverse process. You see, what we have been doing here is we have been doubling up the stresses. So, this is the loading process, and suppose if I start removing the load from 16 to 8, 8 to 4, 4 to 2, 2 to sigma, so this will be unloading. Clear? So, at this point, if I unload the sample, this is how the response looks like. So, this is the loading curve, and this one is the unloading curve, or unloading response. This point is defined as pre-consolidation pressure. And we define this as sigma p prime. This has a lot of interesting, knowledge inbuilt into it. We will discuss about this. This is also known as compression curve, and this is known as swelling curve. This is compression curve or compression characteristics, you may say. These are the swelling characteristics. Now, one interesting thing to observe here is, this is how we started the test with the E naught value. What you observe is that point A and point B will not match. A and B do not coincide. What is the reason? The first reason is because the soil sample is non-linear. Because truly speaking, E upon sigma prime is nothing but a sort of a stress strain curve, is it not? You must have noticed that if I normalize it with the E naught value, this becomes E upon E naught, or I can do even delta E upon E naught, which is the strain versus stress. So, this is first of all because of the non-linearity of the soil. Number 2, regain of, yes, correct. So, what you have done from A to C, you have squeezed out water from the soil sample by applying the external load, and water being incompressible has moved out of the specimen. Now, C to B is a sort of a unloading behavior. Little bit of water can be sucked by the sample, yes, so that is also valid. That is, what we call it as a capillary intake. And which is less than the water which has been expelled out, because the uptake capacity of the soil in compacted form is less. The most important thing is why A and B do not match, because of the friction. So, this is the friction which is offered by the ring, alright. Due to the friction associated with the oedometer ring, which is not allowing B to coincide with A. It is an inelastic material, fine. So, this is known as unloading curve or swelling characteristics also. Now, suppose if I reload the sample from point B onwards, what is going to happen is, this is how the reloading would be. So, B to C to D, ACB is loading and unloading, BCD is, I would say, reloading, or sometimes people also call this as a recompression. Now, one interesting thing here to see is, if I reload the sample from B, it passes through point C and goes up to D. I am sure you will realize that BC has formed a hysteresis, and hysteresis is associated with the memory of the material. So, from this point onwards, I respect soils for having memory. So, this point will get clarified very soon. Soil behaves as if nothing has happened to it, and if you look at ACD, this becomes a continuous curve. So, A to C to D remains a virgin compression curve, as if nothing has happened to it, alright. So, for all practical purposes, I can assume this to be something like this, okay. So, this happens to be its past. All sorts of torture which you have given to the sample goes into the memory and it maintains it. Now, this concept is used quite a lot when we talk about the shear strength theory of the soils. Now, what is the interpretation of C to B to C? So, unloading and reloading cycle, alright. Why we have called this as virgin compression curve? As if nothing has happened to this from this point onwards. So, pre-consolidation pressure is the point, clear, or the pressure above which the sample is going to behave as normally consolidated. We call it as NC response. From this point onwards, you will realize that the material vanishes and the state of stress in the material guides the entire mechanics of the material. So, we do not bother whether this is clay or this is another soil. As far as the pre-consolidation pressure is concerned, that becomes the basic characteristics of the soil mass, which is going to help us in designing the systems. From C point onwards, when you did unloading, this creates the OC behavior of the soil, which is known as this is the OC behavior. We call it as over consolidated soil. Alright. So, by definition, if I define a term OCR, which is over consolidation ratio, clear, if the sigma p prime is greater than sigma prime, at this point what has happened? The material has already experienced a very high effective pressure as compared to unloading part, clear. So, these type of soils are over consolidated, they will show less settlements, less deformation, less compressibility. However, if your sigma prime happens to be greater than sigma p prime, this is the case of the normally consolidated soils, where the deformation, the settlements and the consolidation is going to be much more. Fine. So, what I have done is, by utilizing the concept of the pre-consolidation pressure, I have characterized the soils, and as an engineer technologist, I will be more interested in utilizing the soil mass when it is exposed to the stresses rather than anything else. So, this is the best possible engineering characterization of the soils based on the history of stresses the system has already been exposed to. There is a third category which is known as, so this is the first one, over consolidated response, normally consolidated response, and the third one is, which is known as under consolidated. We call it as a UC. In this case, the present pressure is higher than the previously exposed pressure to the system, sigma p prime, and hence this is NC material. Later on we will link these three things with the pore water pressures. So, in OC materials, normally the pore water pressure is always negative. Why? Because you rightly said they have a tendency to suck water. So, here the tendency of the material becomes to suck as much as water it can uptake or it can suck. So, this becomes a situation where the negative pore water pressures prevail in the soil sample. In NC, normally we have positive pore water pressures. So, suppose if I give you two situations, the soils which are formed in the Himalayan region and the soils which are getting formed in the Sundarban delta, which we discussed in the beginning of the lecture. So, imagine the case of the deltas, every day fresh load of sediments is coming and it is getting dumped into the ocean beds, clear. So, that means the present pressure is always higher than the past pressure. So, this becomes a normally consolidated material. However, in upstream in the Himalayan region, what is happening? The soil is getting eroded day by day, clear. So, the present pressure is always lesser than the past pressure, clear. So, this is the situation of OC material. So, the soils which are in the Himalayan regions are over consolidated as compared to the ones which are in the Bay of Bengal, clear. So, have you understood that from a simple test how much information we have deciphered about the material, and that too in one dimensional compression situation. Under consolidated is the one where the past pressure is equal to the present pressure, is something in between. So, this is what is known as under consolidated response. So, these 1, 2 are normally used in defining the state of the material and how to utilize this as a construction material. If